Morning. In this lecture, in the subject HMA 3322 Discrete Mathematics, we are going to discuss the logics. The main aim of logic is to provide rules by which one can determine whether any particular argument or reasoning is valid. Logic is connected with all kinds of reasoning, whether they be the legal argument or mathematical proofs or conclusions in a scientific theory based on a set of hypotheses. The set of statements in logic are called as propositions. The proposition or a statement is a declarative sentence which has any one or only one of the truth values called true or false. The truth value true is denoted by T and false is denoted by F. The area of logic that deals with proposition is called propositional calculus or propositional logic. Compound proposition means we can form new statements from the existing or given propositions. The given propositions are called atomic statements or molecular statements, whereas the new proposition formed using the logical connectives are called compound propositions. The logical connectives which are used to form new compound propositions are conjunction, or we can call it as and, disjunction or negation or not, exclusive or XOR, conditional statement P if P then Q, biconditional P if and only if Q. So these are the common logical connectives that are used to form new compound propositions. For example, if you take the two atomic statements, it is raining. Q, it is cold. Q, it is cold. So form a new compound statement by combining these two statements. We can use the logical connectives conjunction and disjunction. P and Q. P conjunction Q, it is raining, and the connect here we used is and it is cold. Next statement. Likewise, P disjunction Q, it is raining or it is cold. And here we present the truth tables related to the disjunction, logical connectives. First one is the disjunction, P R Q. So P R Q is false for the combination of both P and Q are false. In other cases, P R Q is true. True, 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 false, true, false, true, true, false, false, false. So we can say that P or Q is false only when both P and Q are false. This is the truth table for disjunction. And exclusive disjunction or XOR we can call. So XOR statement is false for both true and both false cases. That means when P and Q both have same truth value true and truth value false, P or Q forms false, otherwise it is true in the two cases. So you can see that true, true, false, 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 true. In other two cases it is true. And now using the propositions, now we can come to that without using the truth table technique also, we can find out the equivalences. Two propositions are called logically equivalent if they are, for example, A is a statement A is a compound statement, B is a compound statement. Then A is equivalent to B if and only if A biconditional B is a tautology. So here we have some logical equivalences. The propositions P are Q, P conditional Q, and negation P or Q are equivalent. So we can say that the two statements P conditional Q, negation P or Q are logically equivalent. So let us see that how they are logically equivalent. So when we go for the truth table technique, we find that P and Q we have given. Negation P or Q, when we write the negation P or Q, then you will be having that truth values for negation P or Q is true, false, true, true. Likewise, P conditional Q is also, by the definition of conditional statement, the P conditional Q is false only if P is true and Q is false. In all the other cases, it will be true. That's what we have: true, false, true, true. Now we can see compare the third and fourth column. Here we have the logical, the statement negation P or Q, and here we have the statement P conditional Q. So true, true, false, false, true, 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 true. Therefore, both the columns have same truth value in all the rows. That's what we say that these two statements are equivalent, logically equivalent. Likewise, we can say that P conditional Q is the converse of P conditional Q is Q conditional P. And this is the another logical equivalences. We have P biconditional Q is equivalent to P conditional Q and Q conditional P. Now we write the truth table for P biconditional Q. You find that by P biconditional Q is true when both P and Q have same truth value. True, 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 false, false, true. In the two other cases, it is false. Likewise, when you find the truth table for P conditional Q and then Q conditional P, and then when you take the conjunction P conditional Q and Q conditional P, we get that true, false, false, true. Now comparing the two columns, we see that they are same in each row, and hence we say that the two statements are logically equivalent. That means P biconditional Q is logically equivalent to P conditional Q and Q conditional P. And a proposition is called a tautology if its truth value in the last column is set true for all the cases, for every case. For example, when you take P, Q, P conditional P or Q will be having the truth value is true in all the cases. Therefore, this statement is called a tautology or universally true statement. Contradiction means the truth value when it is false in all the cases, in each case, then we call it as a contradiction. Only false in every case. That is called contradiction. And we have some proposition, the formulas you can use the logical connectives and you can prove these two formulas using the truth table technique. Negation P or Q is negation P and negation Q. Likewise, negation P and negation Q is equivalent to negation P or negation Q. This can be carried out using the truth table technique. Now we have a list of formula with us. Using the logical equivalences formulas, we can prove that the statements are logically equivalent or not. Here we have show that negation of P or negation P and Q, and negation P and negation Q are logically equivalent using the logical equivalences. We'll use one of the equivalence tables at a time. Now we take the left hand side, negation of P or negation P and Q. This is equivalent to, we use the De Morgan law for this negation. We have to take it inside the bracket by De Morgan's law. So we apply negation to P. So negation P. This R becomes and for the second term, here the second term is this negation of P and Q. For this we have to take the negation. Again, in the second statement also we are applying the De Morgan's law. That means we are applying the negation inside the bracket. Negation of negation P. Here the AND becomes R, Q becomes negation Q. And we know that by double negation law, negation of negation P is P. So P R negation Q. Then we see that here we have negation, and here inside the bracket we have P R negation Q. So here it is three terms and two different symbols and R. So we apply distributive law for this. Negation P and P R, negation P and negation Q. And we know that negation of P and P is false. False are negation P and negation Q. So false is nothing. False are negation P and negation Q. P or F is P by the dominance law. So we use that here P, negation P and negation Q, R, F is negation P and negation Q. Now we can see that we started from the left hand side and reached the right hand side. Therefore, we can say that these two statements are logically equivalent. Here we have not used the truth table technique, but we used the equivalence laws. We have a list of equivalence laws. From that, we use the necessary law according to this problem. And using the equivalence formula, we can prove that the given statement is a tautology or not. Without using truth table, we can prove this. One more thing is, whenever mentioned in the problem, without using truth table, then we have to use the equivalences. You should not use the truth table technique here. Show that P and Q conditional P or Q is a tautology. So we see that tautology is nothing but the a propositional statement whose truth value is true. So let us consider the left hand side, P and Q, conditional P or Q. Now for the first thing in the equivalences is we have to first convert the biconditional statement if it is in that given statement. If not, next we go to conditional statement. So we have to rewrite the conditional statement. Here we have P and Q, conditional P or Q. So we use this formula. We know that P conditional Q is equivalent to negation P or negation Q. So we see that negation of first statement P and Q are the second statement. So in a conditional statement P conditional Q, P is called the antecedent, Q is called the precedent. So here the antecedent is P and Q. So negation of P and Q are P or Q. Now it is equivalent to, now we apply the De Morgan's law for the first statement. That means negation of P and Q. Negation P or negation Q. Using the De Morgan's law, This is nothing but P R Q. We are not disturbing the second statement. Next we take that negation P R P R negation Q R Q. Just we are using the associative and commutative laws. First we apply the associative law here. Negation Q R P. Interchange these two using commutative law. And then we combine negation P R P or negation Q R Q. So negation P R P is true. Negation Q R Q is true. T R P is true. Therefore, we see that the given statement is a tautology. Next, we take that P conditional R and Q conditional R and P or Q conditional R are logically equivalent. So here also we take the left hand side and we'll try to arrive at the right hand side using the sequence of logical equivalence formula. So we take the left hand side P conditional R and Q conditional R. So we apply the first law, that law we have used here, conditional statement. So whenever conditional statement is here, we have to use the formula P conditional Q is equivalent to negation P or Q. Therefore, P conditional R is negation P or R and negation Q or R. Now we can see that here it's a mistake, it should be R. The same statement R is there. So we apply distributive law here. R, R, negation P and negation Q. Distributive law. Here the left hand side of the distributive law is given and therefore we are using the R, negation P and negation Q, distributive law. And then we use the commutative law, negation P and negation Q R. Again we apply the De Morgan's law for this, the negation P and negation Q. So negation of P or Q R. And again we use this same left hand side to right hand side. Now here the right hand side is given. So we can write the left hand side, this formula. P conditional Q is equivalent to negation P or Q. That means we write this negation P or Q conditional R. Therefore, we arrived at the right hand side. And here also we have the equivalences. P and one more thing is the equivalence symbol may be used this or in this way we can use. Both the symbols we can use to represent the equivalences. Now P conditional Q conditional P is equivalent to negation P. Again first we use the formula P conditional Q. Conditional statement is here. Therefore first we apply the formula for the first term, negation P or Q conditional P. Now you can see that for the second conditional statement, again apply the formula negation Q or P. Now we apply the commutative and associative laws. Negation P or negation Q or P. So we apply the commutative law so that we get negation Q or P or negation P by commutative and associative laws. And we can see that by the complement law or identity law, P or negation P is true. And negation P or true is true by dominant law. Therefore, we see that P conditional Q conditional P is a tautology, left hand side. Now consider the right hand side, negation P conditional Q. Again apply the equivalence formula for negation P. For this conditional statement, when you apply the negation, we have a negation here. Negation of negation P or P conditional Q. And second, we have to apply the same formula for this P conditional Q. negation P or Q. Then apply associative law. P or negation P or Q by associative law. And we know that P or negation P is true or Q. True or Q is true by dominant law. So the left hand side we arrive at a T, and considering the right hand side we arrive at a T. Therefore the left hand side is logically equivalent to the right hand side. And again, use of logical equivalences, we have to prove the following. Negation. Again, the negation symbol may be used like this, or in the symbol where we used in the previous statement. So negation P or negation Q, or negation P and negation Q is equivalent to negation P. Here the right hand side is a single statement, negation P. How we are using it? So if we consider the left hand side, negation of P or negation Q, or negation P and negation Q. Applying the De Morgan's law for the first statement, negation P, R becomes AND. Negation of negation Q becomes Q using the double negation law. And we keep the second term as it is, negation P and negation Q. Next we take negation P and apply the distributive law. See, the common term is negation P here. Here also negation P. Inside the bracket we have AND. Outside the bracket we have R. So it shows that we can use distributive law here. We have same statement negation P and two different statements Q and negation Q. Two different formula, symbol and R. So applying the distributive law, negation P and Q are negation Q. And we know that Q or negation Q is true. And then negation P and true is negation P. That is called identity law. Negation P and T gives you negation P. Therefore, we arrived at the right hand side. So depending on the particular problem, which laws we are going to use. It depends on the particular problem. So that you have to be thorough with the equivalence formulas. Another problem, use the laws of equivalence. Prove the following. P and negation of negation P or Q, or P and Q implies are equivalent to P. Not implies, it is equivalent to P. Right? So let us consider the left hand side. P and negation of negation P or Q, or P and Q. So now you can see that which formula we can apply here means whenever we have negation symbol, we can use De Morgan law. So applying the De Morgan law and the double negation, because for P already we have a negation. For applying De Morgan law, we get another negation. So negation of negation P and R becomes AND when applying De Morgan law. Negation Q, R, P and Q. So P and P and negation Q, R, P and Q. Just we are combining these two statements, that's it. Here we cannot use the distributive law because we have same symbol and here and here. So just we are applying the associative law. P and P and negation Q, or P and Q. And we know that P and P is P by idempotent law. So P and negation Q are P and Q. The second statement we are not disturbing, just we are taking it throughout the derivation. P and negation Q or Q by distributive law. Now, in this step, we can use the distributive law because we have AND inside the bracket, R outside the bracket. P is the common element in the both the statements. Here, first term we have P, second term also we have P. So we have P and negation Q or Q. So P and false, Q or negation Q is true. Sorry, true it is. P and Q are negation true. So P and true. By the identity law, we have P and true is P. So left hand side, from the left hand side, we arrived at the right hand side. Similarly, we can go for the tautology. Negation P or Q or negation P and Q or P is a tautology. Consider the left hand side. Negation of P or Q or negation P and Q or P. Now apply the associative law. Because in both we have R symbol. Here we have R symbol, here we have all symbol. So first we combine the first two terms by associative law. Negation of P or Q or negation P and Q. We keep the third statement there. P. Now we see that negation P and negation Q are negation P and Q. Now you can see that we have two different symbols, and inside the bracket, outside the bracket we have R, and same statement negation P is present in both the terms. So we take negation P and negation Q R Q by distributive law by combining these two. Or the third term P we take as it is. So negation P and true, because Q or negation Q is true, or P. So negation P and true is negation P or P. So negation P or P is true. Therefore, it is a tautology. So this is how we are solving the equivalence formulas using the set of laws or formulas called equivalence laws. So we have a list of formulas starting from commutative, associative, De Morgan, distributive, dominant law, idempotent law, absorption law, negation, double negation law. All these laws will be listed out. You have to be thorough with this. So this is our logical equivalences. And some more examples we have for tautology. Q or P and negation Q or negation P and negation Q is a tautology. We have take the left hand side Q or P and negation Q or negation P and negation Q. Now we can see that applying the distributive law for the first two terms Q or P and Q or negation Q. We take the third statement as it is, third term. And Q or P, and we know that Q or negation Q is true, or negation P and negation Q. And we know that P and T is P. So here Q or P and T is there. Therefore, we write it as Q or P or negation P and negation Q as it is we consider. Now you can see that since we have negation in both the statements, it leads us to use the De Morgan's law. So we use De Morgan law so that we get negation of P or Q, applying the De Morgan law. Therefore, first statement is P or Q, or second statement is its negation, negation of P or Q. We know that P or negation P is at true. Therefore, we arrive at a true. Therefore, the given statement is a tautology. So this is how we have to solve the logical equivalences formulas. Thank you.